This is an overview video for college trigonometry, version 3 from Stitz and Ziegler, 10.6, the inverse trigonometric functions. In a discussion of inverse functions, a couple of concepts come into play. First off, the inverse function. In order for the inverse to be a function, we need to have a one-to-one function to work with. Well, now cosine, because it has periodic, goes over and over and over, is not one-to-one. But if we restrict the domain from 0 to pi, that section of the cosine is one-to-one, and we can then find the inverse of that section. There are other sections that could be used, and this is the one that has been universally accepted. The other thing is the function notation. Here, f inverse is the notation for an inverse function, and that gives rise to cosine to the -1 of x. This notation a lot of people confuse with reciprocal and thinking cosine to the -1 is secant. It is not, it's arc cosine. This book chooses to use the notation arc cosine. So you'd say arc cosine or arc cos, but a better way is arc cosine. So this is the notation you will get to use. So we see this section of the cosine wave between 0 and pi, and when we go to the inverse, we reflect across the line y equals x, switch x and y coordinates, we get this shape. This is the graph of arc cosine of x. The domain is -1 to +1, and the range is from 0 to pi. So you will never get any value outside of an arc cosine. Arc cosine will never give you a value below 0 or above pi. In other words, it'll only give you quadrant 1 and quadrant 2 angles. For the arc sine function, we have to first restrict sine to be 1-to-1. And this is the universally accepted piece, although we could choose other pieces. This is the one that they choose, so this is between -pi² and pi². So in this section, switching x's and y's, we get the arc sine to look like this. Same domain as arc cosine, -1 to 1. And the range is from -pi² to pi². This is negative quadrant 1 angle and a positive quadrant 1 angle. Those are the only values you will ever get out of an arc sine. So all of the properties of arc cosine and arc sine are given in one formula, in one table, Arc cosine, we have the domain, the range. Arc cosine equals t if and only if you are in the correct range, and cosine t equals x. Cosine of arc cosine equals x, assuming your state of the domain, and arc cosine of x equals x, assuming you're in the correct range. So cosine and arc cosine essentially reduce, leaving just x. You can say they cancel, although they're inverse functions, and that's actually what's happening. But you have to make sure you're in the domain and range for these to actually reduce. Same with arc sine, the domain and range is given, and they essentially reduce, assuming you're in the correct domain and range. Additionally, arc sine is an odd function. So some typical examples, they will ask you to find the exact values, i.e. no calculators, of arc cosine of 1/2. So arc cosine of 1/2, what you are looking for is what angle cosine equals 1/2. So you could think cosine of what angle equals 1/2. These are not equivalent statements because this has an infinite number of solutions, whereas this only has one. But we look for, when you plug a positive number into arc cosine, you'll get a quadrant 1 angle out. So in quadrant 1, where does cosine equal 1/2? And the answer would be theta equals pi/3. So arc cosine 1/2 is pi/3 because cosine of pi/3 is 1/2. Now if you plug a negative number into arc cosine, the range of arc cosine is from 0 to pi. So you will get an angle between 0 and pi. So consider that these are the possible answers. You want to find an answer where cosine equals negative square root of 2, and that answer would be here. Because of all students take calculus, we know cosine is negative in quadrant 2. That would be 3 pi fourths. For the sines, arc sine, when you plug a positive number in, you will get a quadrant 1 angle. And arc sine, if you plug a negative quadrant in, you will get a negative 1 quadrant angle. So these, between here and here, are the answers to an arc sine function. So when you're looking for where is arc sine square root of 2 over 2, keep in mind, all students take calculus, sine is positive in quadrant 1. That's where you would get, that would be pi fourths. That's the answer to part B. Now for part D, arc sine of negative 1/2, well, this is where it's positive, this is where it's negative, only cosine's positive. Sine is negative here. Where is sine 1/2 negative? That would be negative pi sixths. So when you're doing an arc sine or an arc cosine, it's very important for you to consider where your answers are going to be. And for arc cosine, it's quadrant 1 and 2. For arc sine, it's quadrant 1 and negative 1. Now for arc cosine of cosine pi 6, cosine of arc cosine, sine, etc., all of these are called composite functions. And when the arc function is on the outside, like E and F, we have to think again, where did, in this case, arc cosine lives in these two quadrants. Now when the inside value is in one of these two quadrants, then the arc cosine and cosine will simply cancel. That's pi 6. However, if the inside function angle is not in these quadrants, then you have to worry about reference angles and other values. So cosine 11 pi 6, 11 pi 6 is right here. 11 pi sixths. That reference angle is pi sixths. And because of all students take calculus, cosine's positive there. So the reference, so if they give us 11 pi 6, the reference angle is pi 6, and cosine's positive, so we have to find the other location with the reference angle pi 6 where cosine's positive, where arc cosine lives, and that's right here at pi sixths. So this value is pi sixths. And that is surprising for a lot of students, that these don't just reduce, because that is not in the range. You can also just evaluate cosine of 11 pi sixths and get square root of 3 over 2. And then find what is arc cosine of square root of 3 over 2, knowing that when you plug a positive in, you get a positive number out, quadrant 1 or quadrant 2, and work it out that way as well. But these definitely have some more challenges to them. For cosine arc cosine negative 3/5, sine of arc cosine of negative 3/5, I think one of the easiest things to do is recognize the arc cosine is an angle. Notice arc cosine of this equals an angle. This was equal to an angle. All of these arc functions are angles. So if you let theta, for example, be the angle, we're looking for cosine theta, where theta is where arc cosine lives, quadrant 1 or quadrant 2. In this case we draw quadrant 2 because it's a negative number. Cosine is adjacent over hypotenuse. We can then fill out the Pythagorean theorem and get 4. They're looking for cosine of that angle, which is negative 3/5. In this case they just reduce, because negative 3/5 is in the domain of arc cosine. Now sine of arc cosine of negative 3/5, basically the same thing, but we're looking for sine of this information. Sine would be 4/5, so this value would equal 4/5. Now there's no quote unquote cancellation here. There was here, but not on this problem. And so it is very beneficial to take an arc cosine and make it into a triangle, and that way you can fill out with Pythagorean theorem and get all the information you need. Hope this helps. Some examples where there's just an x involved. cosine 2 arc sine. So if we do this one for a minute. Again, let theta equal the arc function. So we would have this information. Sine is x, so that would be opposite over hypotenuse, giving us, completing the Pythagorean theorem, the adjacent side. Then cosine 2 theta would be cosine squared theta minus sine squared theta from our identities. We could then figure out what cosine theta is. It would be square root of 1 minus x squared over 1. Square that. What is sine theta? X over 1. Square that. Simplify. This is really the best way I can think of to work out when we don't even know what that value is inside. Express the arc function as a triangle. Use Pythagorean theorem to fill it out, and then you can work on the outside function. For arctangent, we take one cycle of the arctangent so that we can have a one-to-one function. One cycle goes from negative pi halves to pi halves. And so we have this for arctangent. The domain is all real numbers. The range is the same as with the arcsine, from negative pi halves to pi halves. For arccotangent, we take one cycle, and this time one cycle fits nicely between 0 and pi. So the arccotangent function, domain is all real numbers. The range is from 0 to pi, like the arccosine function. So an overview of the properties of arctangent and arccotangent. The domains are both all real numbers. The range from negative pi halves to pi halves. Now it is not including the negative pi halves to pi halves because those are where you divide by 0. So it's not exactly the same as arcsine, but it's essentially the same quadrants. And they will cancel, quote unquote, if you're in the correct range for the arctangent tangent, and they'll always cancel tangent and arctangent for all real numbers. We can also, this is a very nice thing, change from arctangent to arccotangent. What flips is the inside. You'll see this down here. If you have arccotangent and you want arctangent, the inside flips. And of course, there's some restrictions on that because you wouldn't want to divide by 0. Okay, great. An example or two. Let's take a look at one of the harder ones. So let's do D. Sine of arctangent of negative 3/4. So arctangent lives here. And it's negative in the right down here. So I'm going to draw a triangle. Tangent is negative 3/4. And 3, 4, 5 triangle. So we're essentially letting theta equal arctangent of negative 3/4, knowing where arctangent lives, quadrant 1 or quadrant -1. They want us to find sine theta. This is an easy problem. It's opposite over hypotenuse. So this is the kind of work that you can do. Again, if you have an arc function, you can set up a triangle. If the number inside the arc function is recognizable, you can just think, okay, where is cotangent? Negative square root of 3 in quadrant 1 or quadrant 2 where arccotangent lives.